We are building the Fractals and Recursion program from the YByte Python curriculum, available at www.ybyte.in. We have been looking at recursion quite closely. It's clearly quite interesting function calling itself, and we, for example, end up with a pattern of this sort. But there's a valid question: how is any of this useful in practice besides having to, let's say, draw something? Well, it turns out that there are many problems which can be decomposed into smaller problems which have the same structure as the original problem. Now, this looks complicated, but we'll see this from an example. Basically, whenever we have a situation where the problem we are solving is like a bigger version of another problem, there's a natural structure in the whole program, and that's when we can use recursion. Now, again, let's take some examples to try and understand. Let's say we have to, print a countdown. So basically, I have a problem that, I have a problem where, I want to print some numbers which is going from, let's say, 10, 9, 8, 7, 6, 5, 4, 3. Of course, just like in the squares case, we could have, done this with a for loop. That's a fair point. But let's see how we can do this with recursion. Now, for the sake of illustration, I'll compare this to the situation that we have with the square function. Remember, in every function, pretty much, we have a basic task, a recursive call, and then a base case, right? So let's just try to see what's going on here. In the square function, the basic task is to draw a square, and the recursive call is to call to draw a smaller square. So basically, we are drawing a square, and then I call the function to draw a smaller square, and so on and so forth. And I keep doing this until the square becomes too small. So that's kind of becomes my base case, right? So I'll stop recursing at this point. Now, if I were to compare this with the countdown function, the basic task is to print the number. Recursive call is to print a smaller number. So basically, let's say I have a function to print, let's say 9. I can go and say, print for me. The same function can be called to print, let's say 8. The same function can be called to print 7, and so on and so forth. The base case is, of course, when the number reaches 0 or 1, at which point no recursion happens. So I can write this in a recursive manner. I just say, okay, let's say I define a function called countdown, print n. If n is greater than 0, go and call this function once again. Let's see this working. So when I, let's say, come here, let me just write this function here, say def, say count down, say n is in, let's say, an input argument that you provide. So I just go and say print n, I assume that n is positive. I just go and say, look, if n is greater than 0, well, count down, say n minus 1. Now, let's run this to see what happens. So when I run this code, if I just go and do, say, count down, say 10, notice it prints for me 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. And that's really because, this is recursively being called. So when I call, for example, 10, it prints 10, and then it goes and says countdown 9. Countdown 9 prints 9, goes countdown 8. Countdown 8 goes, prints 8, prints, then gets, say, countdown 7, and so on. So again, we notice that this countdown can be seen recursively because from any point, right? Let's say start at 10, basically I have to print the lower number. From, let's say 6, again I have to print the lower number. So it's again one of those problems which is sort of decomposing into a smaller version of itself, and hence recursion could be used. In fact, very interesting, see the similarity between this code and the code we have done earlier. We realize that, when we change the order of, let's say, the basic task, which was square in this case, let's say, so this is the basic task, the square, and the recursion, the order in which the the figure rendered changed. In fact, the same thing can be done here. If I were to, let's say, reverse this whole thing here, it's really quite interesting actually. So when I do this, when I, let's say, run this piece of code, if I, let's say, were to do countdown now, in fact, it will print this in exactly the reverse order: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Because remember, just like as I've shown here, first the recursion is happening, and then the task is happening. So I keep going down into the until I reach the base case. In this case, let's say I keep going down until my n is 1, at which point I go and print, for example, I call countdown 0, and I go and print 0. Then I go and print 1, print 2, print 3, 4, and come back. This is kind of like just to see a comparison. This is the equivalent of, let's say, drawing the squares in the inverted order as we have seen before. Notice here, the smallest square got drawn first, right? So again, countdown, of course, is kind of mimicking that, right? Now, obviously, you might wonder that this looks like an overkill. Why should I use recursion for such a simple problem? But, this is a very good illustration. Clearly, there are many ways of doing it. All I'm showing is that, look, there is a recursive solution as well. let's take another example for this situation. Let's say I have a problem statement where I have to find, say, the sum of, let's say, first n numbers, maybe 1, 2, 3, 4 until n. Now this is a famous, let's say, formula, n times n plus 1 by 2, very useful in mathematics. But a version of this problem would be to find factorial, which is basically 1 times 2 times 3 times 4 times, let's say, n. So that's using, let's say, also used in mathematics. But now this problem is very interesting. Now think about this. S of n is actually n plus s of n minus 1. So notice, seen from outside, seen from, let's say, top, this problem looks like a smaller version. So this, for example, s of n minus 1 looks like a smaller version of the original problem. And I keep going down because s of n minus 1 further decomposes into s of n minus 2, s of n minus 3, and so on and so forth. I, in fact, have a recursive solution. So once again, I have a problem here, which is decomposing into a problem, which is, let's say, a smaller version of itself, right? And so on. So if I were to sort of visualize this, this, let's say, in a recursive manner, if I, let's say, have a function add num, I input to it 5. All I'm saying is that, look, I need to do 5 plus add num 4, because that's exactly what I want to do. And I keep going down until I reach the base case, and then I traverse upwards. So base case returns me 1. I do 2 plus 1. I return that to this function. So it becomes 3 plus 2 plus 1, 4 plus 3 plus 2 plus 1. And then I have 5 plus 4 plus 3 plus 2 plus 1. And that becomes my output. So let's see how we can do this also in recursive fashion. I can just write a function of this sort that, look, if n is equal to 1, this becomes my base case, return 1. Remember, recursion stopped here. If not, then, well, keep, calling the add num, the same function, with a smaller value. So let's just do this as well so that we can, visualize this. So I just go and say, let's say def, say add num, let's say n. I will go and say, look, if n is equal to, say, 1. So if n equals to 1, remember, that's the base case, must be added always. I just go and say return 1. Else, if n is not equal to 1, so n is, let's say something else, I go and say return, say n plus add num, say n minus 1. Notice the function is calling itself. When I, let's say, run this piece of code, so I go and maybe clear this and run this again. If I were to do add num, let's say, 100 is maybe too much, let's say 10, well, I get 55, because indeed 10 times 11 by 2, as we know, is actually 55. And that happened because of the way we wrote the recursion, the way we know the function just keeps calling itself. In fact, we can indeed do, let's say, this, that's 5050. We can try any number, let's say 78, that is 3081. We can verify that 78 times 79 by 2, that is indeed 3081. So, you get an idea. The same function could have been modified for, let's say, for example, a factorial. So there are, a class of problems which basically decompose into, let's say, a structure which is sort of repeats, right? And again, notice this is how fractals come into picture, because fractals are also, structures that basically repeat. So that's why, like I said, recursions and fractals kind of go hand in hand. It's a win-win combination. Fractals, say recursion is a great way to create fractals, as we have already seen. We'll see more. And on their part, fractals are a great way to understand recursion. You saw how we could relate the squares activity to, let's say, this countdown. And that's how this whole thing becomes much more, let's say, visual and good to understand. Before I wrap up, think through this. Is this function safe? In fact, it is not. What happens if I were to give, let's say, a negative input at this? You will realize that, in fact, we have inadvertently created an infinite recursion depth. Because let's say I were to say add num minus 10. Well, I'm never going to get to 1 because I keep going down in the recursion hierarchy. I am in for a trouble here. Of course, we can, fix that by using, let's say, catching try and except. I can say I can assert that n is positive. Or if you want to be simple, you can just have if n greater than 0, then you do all this, right? Just a food for thought. In general, if you think this way of learning where we, build activities, we analyze things in detail, we try to explain things in very simple words, but yet we go in depth. If you think that way of learning works for you, look at our website, www.ybyte.in, because that is how we learn Python programming. Take care. Thank you so much. Bye-bye.